Hey, my wonderful AP students. It's time for a pretty involved video, or maybe even videos, not exactly sure I'm going to break it up, of our fourth topic introduction, dynamic forces. This is going to be pretty involved. In fact, not only are you normally going to write this down in your notebook and write down the questions you want to ask in class, but I recommend about halfway through these videos that you take a break for a little bit and kind of clear your mind, because it's not going to be easy. There's a lot of new words, a lot of new concepts, and things don't exactly adhere to our normal frame of thinking. So the last topics we had were how motion occurs, called kinematics. This is where we looked at accelerations, velocities, things like that. This topic is going to be answering the question, what causes motion? And the answer for that is forces. Forces make things move. Forces make things slow down. And we're going to define a force as a push or pull applied by one object and experienced by another. And the wording in this entire topic, it has to be precise. So as always, you're going to be pausing, rewinding, doing whatever you need to understand this, because I feel that in this video that I'm making here, I'm sending out a lot of good information that you need to know. Otherwise, the advanced part of forces will not make sense. So I'm going to tell you what forces are and how they relate to motion. This video is going to cover how to draw a free body diagram, which is vital into understanding and figuring out both the concepts in mathematics. It will also cover the basic forces that impact motion. You're going to meet like 3 or 4 forces. You're also going to understand all 3 of Newton's laws and see how they relate mathematically and conceptually. The first and last ones are conceptual by definition. The second one is a mathematical one that has concepts inside of it. So, again with the language, we have to be really careful about how our language is with these ideas. It's really easy for you to misinterpret a situation based on the language or wording. Not that's given to you, but how you interpret it and how you think about it. First major misconception. Objects don't have forces, they experience forces. So saying that something has a weight is not true. It experiences a weight. Example, correct sentence. The heavier person experiences a larger force from Earth than a lighter person. Incorrect. The heavier person has more weight than the lighter person. May not seem like much. When we do our force pairs, it will mean the difference. Okay, so when we describe forces acting on an object, we're always going to start with the basic idea of what a free body diagram is. This is a way to create a good picture of the forces, and it'll help you create equations out of nothing. Since with these forces, there's no set equations that we set up every time, and there's no use memorizing what happens in each situation because it's always going to be different. Instead, by using a picture we can create, we can easily come up with the appropriate set of equations and relationships for any situation. There is no use memorizing all these different situations and putting them on the back of note cards. It is about coming up with it to fit the situation. So the first thing you're going to do with this free body diagram is draw a labeled arrow representing each force, with each arrow starting at the object and pointing the direction the force acts. The second thing, you're also going to make a list on the side of all the forces acting on the object. You're always going to list the object applying the force and the object experiencing the force. So you have a picture and a small list near the picture of everything that's going on. Now, in this class, the only forces that can act without touching are gravitational forces and electromagnetic or electric forces. The other forces must be physically touching the object you're looking at, even though what we're really going to say is because the atoms inside all objects always repel because the nucleus is always positive, no things actually touch. There is always forces acting at a distance. So right now when you're sitting in your chair or whatever listening to this, you realize that the atoms in your butt are actually kind of hovering over the atoms in the pants that you're wearing, which are also hovering over the chair that you're sitting on, and the chair wheels or legs are also hovering above the ground. There is no actual atom-to-atom contact. which is freaking awesome. So, before we continue this picture, let's make a small list of some forces that we're going to see. The first one, we're going to call weight. That's the force of a planet on an object near that planet. When you're in outer space, you have virtually zero weight. It's not exactly zero because we're going to see gravity pulls off for a really long distance. So on this planet, you have weight because the Earth is pulling you towards it. There's also a force of friction. Force of friction is the force of a surface on an object. It acts parallel to the surface. So if you're sliding to the left, friction's acting in the X direction. If you're falling down a ramp, the friction is not X or Y, but direction of the ramp. There are two types of friction. The first type, kinetic friction. The frictional force when something is moving, it always acts the opposite direction. So if you're sliding downhill, the frictional force, kinetic friction, is uphill. And the second one is static friction. Frictional force between two surfaces that are not moving. So kinetic is when it's moving and it's opposite direction you're moving in. Static friction, you're not moving, it's just there kind of keeping you locked in place. And finally, normal force. It's also a force of a surface on an object, but it acts perpendicular to the surface. A way to think about it is, right now you're sitting in a chair. The Earth is pulling you down, that's your weight. The chair is pushing you up, perpendicular to its seat. That's the normal force. So let's do this free body diagram example using those 3 points we just wrote down and these forces we just described. A car is moving right on the beltway, and it applies the brakes and skids to a stop. Draw and label the forces, not components, that act on the car to slow it down. So with this example, step 1, draw the object you're focusing on. There's my car. It is pretty. Step 2, if it's on or near the Earth pulls on the car. It is not gravity. Let's not call it that. The force is called weight. Let's add it in. And again, let's take a little note on the side. Weight, the force of the Earth on the car. Number 3, all the other forces we're going to draw here must be the result of the car touching things. What is the car touching? Well, simply, it's touching the ground. So the ground's going to exert a normal force perpendicular to the surface. Since the car is going right, the ground is level. You have an upward normal force, the force of the ground on the car. And since it's sliding on the ground, there's also friction here. And it's kinetic friction. And it's the opposite direction of motion, so it's going right. Then the force of friction, I'm going to call FF. Just like FN, I'm going to call force normal. Even though you could literally write the words here, you can choose whatever you want for them. These are just kind of common symbols. The force of friction right here is the force of the ground on the car. So the ground's got two different directions, a Y force and an X force. And we're done. Wait, what? The car's moving right, dude. There must be a force to the right making it go forward. Nope, 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 nope. The car is moving to the right. The car is not in contact with anything pushing it forward. And the car is going forward because sometime in the past, there was a force that made it go forward. This picture is only about that moment in time. At that moment in time, the only forces in the X direction are the friction backward, which is why it's slowing down. And that amount is unbalanced. There's an unbalanced force in the opposite direction of motion. From the force point of view, it does not know if it's going forward or not, and it doesn't care. Remember Zeno's paradox here. The car doesn't remember previous motion. It's moving to the right, but there's nothing physically pushing it to the right. It's only going right because it had right motion in the previous moment. And eventually, in some time, if nothing changes, it will slow down and stop because its forward motion is being taken away by the backwards force. So a big note about free body diagrams. If there are forces acting in both X and Y directions, the smart of you will call that something at an angle. We're going to draw two free body diagrams. One that has the vectors without breaking them down, You can see right here, for example, I put a leash on my cat. I'm trying to drag it forward, but I'm pulling up at this angle. You can see I put pull, the force of the person on the cat, because I'm pulling up. The other one you're going to draw afterward, and next to it has the vectors in their x and y parts. So I took that angle, and it's like you're being pulled in x, forward to the right, and pulling up in y. Pull x, the force of the person on the cat horizontally. Pull y, the force of the person on the cat vertically. So now let's go to Newton's laws. There are 3 of them you're going to learn today. The first law. An object in a state of constant motion, including zero velocity, that's constant motion, just sitting there, will continue in that state unless acted on by an unbalanced or net force. The phrase unbalanced or net are like our key phrases for this entire unit. That constant motion occurs when the forces are in equilibrium. That means that the forces experienced by an object are balanced, so they're equal in opposite directions. When something's in constant motion, it either has no forces at all working on it, or the forces working on it are all balanced. So there's no amount of unbalance, there's no amount of net force. Here's my phrasing. When in equilibrium, stuff keeps doing what it's doing. So, the property of objects that allows them to stay at rest until there's an unbalance of force making a move, like for example, your textbook, is going to stay on your desk forever until there's an unbalance that makes a move. For example, let's say like you give it a shove, or the table breaks, and that time there's no longer a table pushing it up, so the weight will have it go down. Or the property of objects to keep going at constant velocity until an unbalance of force will speed it up or slow it down. So for example, my car's in cruise control. It will keep on going at that 55 miles per hour until it either speeds up or slows down because of an unbalance of force. This property that allows things to do it is called inertia. And it's represented by the resistance of an object to its changing state of motion. In other words, its mass in kilograms. The bigger something is, the more it resists changing its motion. You blow on a very light piece of paper, it'll move. If you blow on a heavy rock, it won't move. Plus, if a rock's rolling down a hill, it's very hard to get it to slow down and stop because it wants to keep rolling down the hill. If you have a small pebble rolling down the hill, it's really easy to have it come to a stop because it has less inertia. Newton's first law is sometimes called the law of inertia. Here's the cool thing. Once something is moving at a constant velocity, for example, not moving at all and moving at the same speed, you don't need a force to make it do it. It will keep doing it on its own because of its inertia. You just need to have an unbalanced force to change what it's doing. And it's all about change. So now I'm going to close this video, and the next video we'll talk about the second and third law.